temperature is the biggest enemy of power semiconductor, and handling thermal management is the biggest design challenge for high-performance systems.
Hello and welcome to the podcast for engineers. This is the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. I'm your host, Peter Balint, and today we continue our journey into the world of powering AI. And with us today is Davide Chiola. He's a VP of System Solutions here at Infineon. And welcome. Thanks for coming in today.
Thank you, Peter. Thank you for having me here today.
We've talked a lot about the power required for these AI data centers. And there's a lot of things that go hand in hand. And one of the things that go hand in hand with the power is the thermal effect. So, and managing this thermal energy. So, to kick things off, can you give us an idea of how much really if you look at the total cost of ownership in a data center, how much of that is devoted strictly to thermal and cooling?
Sure. So, Peter, let me start before I address directly your question. Let me start with a small information about a city called Luleå. I hope I pronounced the name correctly. It's located in Sweden, in the north of Sweden, actually close to the North Pole. And Luleå became famous in the 2010, around 2011, because it was the first data center installation of Facebook outside the US. Now, what is special about Luleå is that the average temperature during the year is 1 degree Celsius. Temperature can go down, of course, in winter to -20, -30, and in summer, never less than 10, 12 degrees. So now you understand how important is thermal and management and cooling and cool weather for data center installations. Now, going specifically to your question about total cost of ownership, so TCO. Typically, it consists of two elements. So there are fixed costs like CapEx, capital invest, so how much fixed investment we have to run, as well as OpEx, so operational expenses. So how much do we have to spend every year to maintain and operate the system? So for a typical AI data center, the part related to cooling, meaning, let's say, air conditioning infrastructure, for example, for the CapEx, or paying the electricity bill related to cooling for the OpEx can be significant. And to give you an idea, this can be in the range of 30%. So on a large installation of, let's say, 2,000 racks for AI, 1,000 to 2,000 racks, which is a relatively large installation, which cost somewhere around 100 million, can be, of CapEx, and an OpEx in 10 years of around 50 million. Then we can think about 50 million, 45 to 50 million, so 30% devoted to cooling aspects. So really relevant. In fact, if we map a little bit the installations across Europe or US, we see a lot of them in relatively cold climates. So Ireland, for example, Netherlands, Sweden, as I mentioned, in US, in Canada also. So definitely cool climate plays a big role in data center installations, yeah.
Okay, so you could leave the windows open, basically.
Pretty much. Actually, in this Facebook data center, there is hardly any air conditioning, cooling, but it's really big fans that are flowing cold air from the outside into the facility. So that's the idea.
Okay, and then let's zoom in a little bit and look at something like a power supply.
Yes.
In an AI data center, which is something you're focused on. And let's be even more specific and say the 8 kilowatt power supply unit from Infineon. When you look at the designers' challenges, what are the biggest things that they have to overcome in the design of these power supply units?
Yes, Peter. So again, before I talk about that, there is another important aspect in the TCO. I want to step back 1 second on TCO, which is the investment for real estate. So again, real estate can be a big deal. The cost depends on the location. Of course, in highly populated urban areas, this is more expensive. In remote location, is less expensive. But this can also end up to something like 15 to 20% of the total installation cost and maintenance cost. That means that the two aspects are somehow related. So cool climate, but also having a limited real estate, meaning density, is an aspect that has to be taken into account when thinking about a data center construction and installation and operations. Now, if we think about our systems, so particularly a power supply unit, that is one of the components of the power conversion in the overall conversion chain, main aspects that we should take into account, I will consider, again, density. Density is very important for what I mentioned. Managing temperature as well, as we just mentioned, and efficiency. So these three elements are somehow related with each other in a sort of trade-off, meaning that typically high density means higher temperature. So if we compress the system, of course, the heat has less space, less surface to dissipate, so temperature tends to go up. If we, at the same time, increase efficiency, then we can compensate this effect. So typically, a more efficient system can have higher density and also lower temperature of the components. What I have here today are two system solutions for server data center. The specifications are very similar. So both are 3 kilowatt rating, 3 kilowatt power. They have an efficiency of around 97.5%. However, as you can see from the sides, the density of the two solutions is totally different. So the one on top is, let's say, a traditional design approach, having around 30 watt per cubic inch power density. And the one on the bottom here is using all these design measures that I described for a quite advanced power density of around 100 watt per cubic inch. The construction is quite different, and I would like to highlight just, for example, the size of the electrolytic capacitor that are playing a big role, as you see, in volume and space, and also the distribution of the component that here was optimized by a simulation method and by advanced integration that enabled this high-density approach.
And if you don't see video now, you should know that there's quite a bit of a size difference going on here, right?
Exactly. They are significantly different, and I can tell you, Peter, that now in the size of this older 3 kilowatt design, we can squeeze actually an 8 kilowatt output power.
Amazing.
So now from the design side, so if we have to design a typical system, so how do we take care of these elements? There are many aspects to consider. For example, for the system that you mentioned, this latest 8 kilowatt power supply unit that we developed for AI data center, simulation, so the theoretical approach first is the starting point. So for what concern thermal management, airflow simulation has to be carried out. Consider that these systems are normally included in a rack, and they are stacked on top of each other or near each other. So there is no way to dissipate heat vertically or laterally, but rather only longitudinally. So there is a fan actually on one side that flows air. So the way the air is distributed, so the air distribution and how many obstacles are found during this airflow is very important. So simulation of the airflow, placement of the component, making sure that there are no hot spots or no barrier to the airflow, even considering power dissipation. So a system like the 8 kilowatt system runs a 97.5% efficiency. This means that around 200 watt are dissipated in power. A fan like this one can consume up to 20-30 watts. So this can be up to 10% of the total losses. So if we blow air too fast, we cool down the system, but we consume a lot of energy. So this is, counterproductive for the efficiency. So this has to be carefully considered. Another aspect that we should take into account in improving this trade-off that I mentioned is the reduction of the passive components. If you look at a traditional system like the one we have on the table, the electrolytic capacitor that you see here are taking a big space. If you look at a more modern system like the one I have in front with a much higher density, you can see that the size of the electrolytic capacitor is strongly reduced. This can be done by basically special circuit, special topologies, Particularly in this new system, we have a power conversion element here, which is called hold-up time extension circuit, that basically by using silicon components, highly efficient, we compensate somehow the size of the electrolytic cap. So by having this extra small circuit, we can reduce the size of the electrolytic capacitor, for example. Another very important aspect is integration. As mentioned, density comes with highly integration. And here I want to bring also one example, which is the magnetic integration in one of the conversion steps, which is the LLC resonant converter. So the system is made by a passive component, which is basically a transformer, a magnetic inductor, and a series resonant inductor. Typically, in a conventional system, these are components placed separately on the board. In an advanced high-density system, we have an integrated design where the primary and the secondary part of the transformer are integrated in the PCB, and the magnetizing inductor is placed on top. So this is a way to integrate basically the magnetics. And in the latest integration, we also integrate the so-called synchronous rectifier, which is one additional components that we need to complete the secondary side of the system. So high integration contributes, of course, to high density. And the special design that you see here is having like a radiator effect. So these PCBs are exposed to the airflow and increase the area exposed to airflow to improve the cooling, basically, capability. Finally, very important also here, topology. So topologies are important to increase density. Advanced topology can help to reduce the stress on the power components and also to reduce temperature. Basically, better efficiency means better thermal management and lower temperature. So summarizing again, optimized design of the airflow, reducing the size of the electrolytic capacitors, integration, especially integration of magnetics, and special topologies and semiconductor quality, of course. This standard solution uses mainly silicon and silicon carbide components. This advanced solution is basically completely based on wide bandgap semiconductors. So GaN, silicon carbide switches.
Okay. And in addition to all of the design challenges, I'm quite certain that there are standards that are given that if you want to sell something in the marketplace, you have to be at this point temperature-wise and efficiency-wise.
Correct. There are standards. So let me say that in general, temperature is an enemy of power semiconductor, independently of the system. So temperature is the main acceleration factor for most of the degradation effect in power semiconductor. If you think about gate oxide, if you think about interconnects, so packaging, so they're all very sensitive to temperature and especially temperature variation. So we want to keep these two elements down, absolute temperature and also temperature swing as small as possible. Now, there are standards. One standard driving the server for data center is the OCP, so Open Compute Project. One variation of the standard is talking about operating temperature for the power components should stay below 10 degrees below the maximum temperature, maximum junction temperature. And another standard, which is quite known, refers to the temperature difference of the airflow. So the airflow between the input and the output should not exceed 20 degrees. So in order to, this means that the whole system has to, dissipate low enough to not to increase the temperature beyond 20 degrees, basically.
Okay. And when it comes to trends, you're out there, you're in the field. What kinds of trends can you identify that are happening in this area of thermal management?
Yes, we can definitely observe trends regarding the cooling and the thermal management. So one very clear trend already visible is liquid cooling. So as mentioned, these systems are now airflow cooled. So you see an airflow, a fan and an airflow. However, if you go to rack power on the 100, 200 kilowatt per unit up to 1 megawatt, which is what the major OEMs are having as a goal, airflow becomes not effective any longer, not so effective. So liquid cooling is already a state-of-the-art for some part of the system. For example, the so-called IT trays are normally running on liquid cooling. And there are ideas about having also this component or a test, let's say attempt, to also have other part of the system cooled down by liquid cooling. So liquid cooling can greatly improve the so-called power usage effectiveness index, which is an index of how effectively the input power is used to computational power. So an index of 1 would be that the entire power is used to do computation, which is what these data centers are about. So by the elimination of fans and chillers, which are mechanical elements of a typical airflow infrastructure, this index can be brought below 1.1, which is very good. And that means there are some tests done, for example, for some of our ODMs, a temperature reduction of up to 40% for the power component, typically. So it means components that run at typically 100 degrees C, they can run at 60 degrees C with a good liquid cooling system. Liquid cooling, there are different technologies, of course. There is this so-called cold plate, which are the one more, again, known at the time today, already in use today, which basically means the converter is sitting on a surface which is cooled by liquid, and the heat is extracted by this cold surface, up to even more efficient system from a thermal point of view, which is immersion cooling. So this is very interesting. Basically, the entire converter is immersed in a bath, in a liquid, which is a sort of oil with high dielectrics. And this allows a heat extraction, even more efficient heat extraction. However, of course, there are also a reliability risk. So this is a technique still, let's say, in development at the moment. At Infineon, by the way, we are looking quite actively at that. So these, I would say, are the short-term innovation in thermal management and cooling that we see. If I need to look, I can look a little bit beyond that. There are also, of course, research areas where big benefit can be found also for this kind of application. So one is in superconductor. So everybody knows that when current flows in a conductor, dissipates heat. There is a law, it's called Joule effect. And this heat dissipated is proportional to the resistance of the conductor. And by the way, to the square of the current. So system with high current, they tend to dissipate more heat, of course. Now, that means that if we could lower the resistance of the conductor, then the dissipation would be much lower, so the temperature increase would be much lower. And there are interesting materials that if they are cooled at very low temperature, however, close to the liquid helium, so very few degree Kelvin, they show basically zero resistance. So they will have zero dissipation. So current flowing through them will have zero dissipation. Unfortunately, of course, this is very difficult to achieve because it's very expensive also. But there are already a commercial system like the magnetic levitation train in Japan, for example, or the MRI, so the magnetic resonant system in the medical industry that are based on this principle. So already working on this principle today. So the dream in power electronics would be that a superconducting electronic would be available. And there are now research studies showing that there are materials showing superconductivity effect even to higher temperature, even close to room temperature. But in this case, you need a lot of pressure. So you need to contain this system into a lot of high pressure. So very challenging. So to answer your question shortly, I think the next frontier, the next step is probably superconductivity, but we need a better cryostatic technique, so cryogenic technique to reach this superconductive state for the metals. Yeah.
All right, very well put. So do you have any last words today?
Well, I can just say, Peter, it's a very exciting time because we are at the verge of a technology revolution, technology transition and revolution that doesn't happen very often. So I think we, as Infineon, we are proud to be part of this race, to be part of this game, and we participate, in many aspects. And basically, this is what I think motivates me as an engineer, as a leader in Infineon. And we try to bring this innovation and this value also to our customer through our improved system solutions. Yeah.
Thank you so much for coming in today and sharing your knowledge with us.
Thank you, Peter. Thanks a lot.
And to our audience, I say thank you for dropping in today. And if you would like to submit any questions or ideas for future episodes, please feel free to send an email to wepowerai@infineon.com. Thank you, and see you soon.